Good day, everyone. We're here to report on our expository project in topology. I am Razel Ann Curiba together with Sir Rodel B. Cotayan. This article is entitled New Structure in N Topology by V. Ramesh et al. So we have first definition 3.2. Let X be a non-empty set, tau sub 1 and tau sub 2 be two arbitrary topologies defined on X, and the collection 2 tau be defined by, we have 2 tau is equal to the set S subset of X, where S is equal to the union of A sub 1 and A sub 2, union of B sub 1, union of B sub 2, where A sub 1, B sub 1 is an element of tau sub 1 and A sub 2, B sub 2 is an element of tau sub 2. Satisfying the following actions, we have number 1, X, a non-empty set, is an element of 2 tau. Number 2, the union of S sub I, where I is equal to 1 to infinity, is an element of 2 tau for all S sub I, an element of 2 tau. We have number 3, the intersection of S sub I, where I is equal to 1 to n, is an element of 2 tau for all S sub 1 is an element of 2 tau. Then the pair X and 2 tau is called a bitopological space on X, and the elements of the collection 2 tau are known as 2 tau open sets on X. We can generalize the above definition as given. So we have let X be a non-empty set tau sub 1, tau sub 2 up to tau sub n be n arbitrary topologies defined on X, and let the collection n sub tau be defined by this equation. So satisfying the following actions. We have 3 actions. X, empty set, is an element of n sub tau. Number 2, union of S sub I, where I is equal to 1 to infinity, is an element of n sub tau for all S sub I is an element of n sub tau. So number 3, we have the intersection of S sub I, where I is equal to 1 to n, is an element of n sub tau for all S sub I, element of n sub tau. Therefore, X 2 tau is bitopological space on X for n is equal to 3, and assume tau sub 1 open in X is equal to X, null set, and A. We have tau sub 2 open in X is equal to X, null set, and BD. And tau sub 3 open in X is equal to X, null set, CD, then 3 tau open in X is equal to X, null set, A, D, AD, BD, CD, ABD, ACD, BCD, and 3 tau close in X is equal to X, null set, A, B, C, AB, AC, BC, ABC, BCD. So therefore, we have X and 3 tau is a tritopological space on X.
Good day! I am Rodel B. Cotayan, groupmate of Ms. Razel Ann Curiba, and assigned in the other definition given by the article of V. Ramesh entitled The New Structure of N Topology. To start with, we have definition 3.7. Let X be an empty set and S be a subset of X. Then we have letter I, and first, the bitopology interior of S is denoted by 2 tau minus and S, and defined by 2 tau and S equals the union of G, where G is a subset of S and G is 2 tau open. Letter B, we have the tritopology interior of S, denoted by 3 tau interior of S, and defined by 3 tau and S equals the union of G, where G is a subset of S and G is tritopological space open. And letter C, generally with these two, A and B, the n topology interior of S is denoted by n tau, n sub tau, and S, and defined by n sub tau and S is equals to the union of G, where G is a subset of S and G is n topological space open. We have here number 2, or the second. A, the 2 tau or bitopology closure of S is denoted by 2 tau CLS and defined by 2 tau closure of S, where the intersection of F, where S is a subset of F and F is 2 tau closed. Letter B, we have the 3 tau or tritopological closure of S is denoted by 3 tau CLS and defined by 3 tau, the closure of S, equals the intersection of F, where S is a subset of F and F is 2 tau closed. Generally, with this A and B, we have n topological closure of S, denoted by n sub t tau minus CLS and defined by the n topological space closure of S equals intersection of F, where S is a subset of F and F is n sub tau closed. After that one, after the two definition, we have here the theorem 3.8. After this definition 3.2 and 3.7, given that example 3.3, remark 3.4 and 3.5, we have here theorem 3.8. Let X and NT be an n-topological space on X, and let A and B a subset of X. Then, letter I, we have n-topological space with a smallest close containing set A. We have here n sub t minus CL A. That is what we call the smallest n topological space closed set containing A. A is n topological space closed if and only if we have n sub t minus CLA equals A. In particular, n sub tau minus CL containing null is equals also to null, and n sub tau minus CLX is equals to X. We have number 3. A is a subset of B. It implies that n topological space A set A is a subset of B, which implies that n topological space containing set A closed is a subset of n sub tau minus CL of B, or closed set of B. Number 4, we have n topological space minus the closure of A union B is equals to n topological space minus the closure of A union n topological space minus the closure of B. And we have here second to the last. Number 5, n sub tau or n topological space closed in A intersection B is a subset of n topological space minus the closure of A, intersection n topological space minus closure of B. And the last we have number 6, n topological space minus the closure of n topological space minus closure of A is equals to n topological space minus closure of A. That was number 6 for theorem. For the proof of that theorem 3.8, we have since the intersection of any collection of n topological space closed sets is also an n sub tau closed in n sub, then n sub tau minus the closure of A is n sub tau closed set. Trivially, set A is a subset of n sub tau closed containing A by definition of n sub tau closure of A. Now let B be any n sub tau closed set containing A. Then n sub tau closed containing A is equals to the intersection of F, where A is a subset of F and F is n topological space closed subset of B. Therefore, A is the smallest n topological space closed set containing A. Number 2, we have assume that A is n topological space closed, then A is the only smallest n sub tau closed set containing itself, and therefore n sub tau closed containing A is equals to A. Conversely, assume that n sub tau closed set containing A is equals to A, then A is the smallest n sub tau closed set containing itself. Therefore, set A is n sub tau closed, particularly since null and X are n sub tau closed set, then n sub tau closed containing null is equals to null, and n sub tau closed in X is equals to X. Assume that A is a subset of B, and since B is a subset of n sub tau closed containing B, then A is a subset of n sub tau closed in B. Since n sub tau is closed in A is the smallest n sub tau closed set containing A, therefore we have n sub tau closed containing A is a subset of n sub tau closed containing B. We have here number 4 proof. Since A is a subset of A union B and B is a subset of A union B, then by the proof number 3 we have n sub tau is closed containing A union n sub tau closed containing B is a subset of n sub tau closed containing A union B. On the other hand, by proof number 1 or I, A union B is a subset of n sub tau closed containing A union n sub tau closed containing B. Since n sub tau is closed containing A union B is the smallest n closed set containing A union B, then n sub tau closed containing A union B is a subset of n sub tau closed containing A union n sub tau closed containing B. Therefore, we have n sub tau closed containing A union B is equals to n sub tau closed containing A union n sub tau containing set B. We have here number 5 proof. Since A intersection B is a subset of A and A union intersection B is a subset of B, then n sub tau closed containing A intersection B is a subset of n sub tau closed containing A intersection n sub tau containing closed containing B. We have here the last proof. Since n sub tau is closed containing A is n sub tau closed set, then n sub tau is closed containing n sub tau closed containing A equals n sub tau closed containing A. We have here, that was the proof of theorem 3.8. We have here an example. Let X be AB's set A, B, C, D for n is equals to 2. Consider that tau sub 1 open in X is equals to the set X, null, set A, set BD, set ABD. And tau sub 2 open in X is equals to X and ta X and null, I mean. Then, the bitopological space tau sub 2 or tau sub 2 open in X is equals to X null ABD and lastly ABD. Also, bitopological space closed in X is equals to X null set C AC BCD. Let set A is equals to a singleton A and B is equals to a singleton a set BC. Then bitopological space closed set containing A is equals to AC. And bitopological space set containing B is equals to BCD. And the last, we have bitopological space closed A containing A union intersection B is equals to null set. Therefore, bitopological space closed A union B is not equal to bitopological space closed set containing A intersection bitopological space closed set containing B. That is, equality does not hold in proof 5 in theorem 3.8. And that was our topic as we have here the article given by V. Ramesh et al. That would be all and thank you for watching.